In this video, we're going to find the open intervals where this function is increasing or decreasing. We're also going to find extrema using the first derivative test, and then we're going to graph the function. So let's start by finding the intervals where f is increasing or decreasing. The first thing you need to do is find any x values, or find the domain of this function. Because that domain is going to determine the intervals where the function's defined. And you want to classify f on those intervals. You want to classify it as either increasing or decreasing. So first we find the domain. Always find the domain first. And remember, you want to rule out x values that cause these three problems. You don't want to divide by 0. You don't want even roots of negative numbers, because those would be complex numbers and we're not interested in those in this class. And we don't want to take logs of negative numbers or 0, not in this class. Okay. So I notice I don't have any logs. I don't have any division by 0. Now I do have a root. Remember what this root is. If you have x to the n over, or m, that's fine. The number in the denominator, that's the index of the root. That's the mth root of x to the n. So this is really, since that's a 3 there, this is the cube root of x plus 3, all raised to the first. So that's an equivalent to that. So this is really a cube root function, even though it's written as a 1/3 power. Okay. I don't have any division, I don't have any logs, and I don't have any even roots. I've got an odd root, but odd roots are well defined for all real numbers. You can take the cube root of a positive number, a negative number, or 0. Remember, cube root of -8 is -2, because -2 cubed is -8. So yeah, this is well defined for all real numbers. So our domain is every real number. That's great. Or we could just write it like that, the R with the double bars. Okay. After you've found the domain, if you want to find the intervals where the function's increasing or decreasing, you need to think about where the derivative is 0 or where the derivative is undefined. So we're going to find our critical values. Because those x values where the derivative is 0 or the derivative is undefined, those mark the endpoints of those intervals where the function could go from increasing to decreasing, decreasing to increasing, increasing to increasing, decreasing to decreasing. Those critical values are where the function starts to change behavior. So we need to find those. Remember how we find the critical values. You're going to set f prime equal to 0 and solve for x. And then you also want to consider x values that cause f prime to be undefined. As if f prime is undefined or if f prime equals 0, we've got a critical value. So first thing we need to do is take the derivative. And notice I've got a composition of functions. I've got this inside of that function. The derivative of this composite function is the derivative of the outside, so you bring the power down, multiply by the inside function to the 1 less power. 1/3 minus 1 is -2/3. And then you multiply by the derivative of the inside by the chain rule. Derivative of the inside is 1. Now if I leave it like this, and I set f prime equal to 0, I might make an algebra mistake. A lot of students do with a problem like this. So I always tell them, if you see a negative exponent, and you've got an x in the base like this, you want to rewrite it. It'll just make it a little bit clearer what's going on. So remember, here's my properties. If you have x to a negative power, that's the same as 1 over x to the same power but positive. So that's what we have right here. I've got 1/3, and then this is 1 over the quantity x plus 3 raised to the positive 2/3. And if I multiply straight across, I get this. It's much more obvious. Okay, now at this point, we want to set f prime equal to 0 and solve for x. Now I already know, since there's a 1 in the numerator, there's no way this is going to be 0. There is no x value I could put in that denominator that would cause this fraction to be 0. Now if you don't believe me, you can set both sides equal to 0 and solve for x, or try to solve for x, by multiplying by the LCD. Well, what would you get? You'd have this over this equals 0, and so we multiply both sides by the LCD, which is the original denominator. And you're saying to yourself, yes, I get some cancellations, that's why we multiplied by the LCD. But watch what happens. I've got 0 times something equals 0. Is 1 ever equal to 0? I hope you're like, oh no! No, don't do that. Can't do it. Since this never happens, the derivative is never equal to 0. Okay, so we don't have any critical values that come from the derivative being 0. Now we also have to think about when f prime is undefined, and they have to be x values in the domain. I guess I needed to say that. Consider x values that cause f prime to be undefined. These are in the domain of f. It's very, very small, sorry. Okay. Are there any x in the domain that cause this to be undefined? So, well, yeah, the domain was all real numbers, and I've got an x in the denominator now. So we know that f prime is undefined when its denominator is 0. And the only way this will be 0 is if x plus 3 equals 0. So x plus 3 is 0 when x equals -3. So that is our one and only critical value. Okay, what was the question again? Oh yeah. Our goal was to find the open intervals where f is increasing or decreasing. That was the first question. So we found the domain, we find the critical values, and then you're going to sketch the critical value. In this case, there's only one, on a number line. And then we're going to determine the sign of f prime on each of those intervals. The intervals determined by the critical values. Interval. Okay, so here's my number line. There's -3. Here's f prime. And f prime was 1 over 3 times the quantity x plus 3 to the 2/3. Now, I find in this case it's helpful to rewrite this, even write it differently one more time. We're going to use this property again. So I've got that fraction power. The number in the denominator becomes the index of the root. So that is a cube root, but that number in the numerator, that gets applied to this expression, this x plus 3. So this is really the cube root of x plus 3 quantity squared. If I write it like that, it's really obvious what the sign is of f prime on every interval. F prime is undefined when x equals -3. I'd have 1 divided by 0, which that's not possible. We can't do that. But remember, as the denominator gets closer and closer to 0, we're going to get closer and closer to positive or negative infinity. But if x isn't -3, to the left of -3 at -4, let's say, -4 plus 3 is negative 1. Negative 1 squared is positive 1. So I've got the cube root of 1, which is 1. So I end up with a 1/3. So when x is negative 4, we get a positive number. When x is negative 3, or negative 3, it's undefined. When x is negative 2, negative 2 plus 3 is 1. So this is, of course, 1 times the 1 in the denominator times the 3, and you get the 1/3. So we're going to get the same value on either side at negative 4 and at negative 2. So we get a positive over here, a positive over here. Okay. And at negative 3, our slope is undefined. But notice we get a 1 divided by 0, which we know is approaching infinity. Okay, so the question said, find the open intervals where f is increasing or decreasing. Well, it looks like it's never decreasing. It's only increasing. On this interval, it's increasing because the function is increasing when the derivative is positive. The function's increasing over here as well because the derivative is positive over there. Okay, so let's answer the question. The original function f is increasing on the interval from negative infinity to negative 3 and negative 3 to positive infinity. Read that number line from left to right. Yes, I'll say f is never decreasing. And we know that f prime is undefined at x equals negative 3. Okay. Now the second part of this question, it wasn't written up there, but the second part of this question could have been and would have been, okay, after you answer that, find all the intervals where the function is increasing or decreasing. Now I want you to, so this is part 2 of your question, find any relative extrema of the function. Does the function have any relative mins or maxes? Well, according to the first derivative test, we only have relative extrema when the derivative changes signs. And it looks like our derivative goes from positive to being undefined to being positive again. So we have no relative extrema. It has no relative extrema on its domain. I don't know why I wrote relative twice. And I'll just give myself a reason, because f prime never changes signs. It would have to change signs for us to have. I don't know why I'm writing the wrong thing over it. Never changes signs. There we go. It's getting late. It's probably a sign it's time for me to go to bed. Okay. So f is increasing on these two intervals, it's never decreasing, and we have no relative extrema. The last part is just where we graph the function f. And our graph should tell us something. It should be consistent with everything that we just talked about. And remember, the 1/3 power is the same as the cube root. So without using calculus, just using what I know from pre-calculus, I can graph this function. This is the cube root graph shifted 3 units to the left. When x is negative 3, we get the cube root of 0, which is 0. So remember your cube root graph, it kind of looks like this. Isn't that consistent with everything we just talked about? It's increasing over here, then it's increasing over here. Now, if you're wondering, what is that with the f prime being undefined? Isn't that smooth? It is smooth, but if I draw the tangent line, that tangent line is a vertical line. It's just the line x equals negative 3. Well, vertical lines have undefined slope. That's what we told you guys back when we studied slopes in algebra class, right? Well, what does that mean in terms of our limits? If this derivative is the slope of the tangent line, Like, when would I get a vertical tangent line? Well, if we compute that limit, the limit as h approaches 0 of f of x plus h minus f of x all divided by h, if we do that limit that defined the derivative at x equals -3, it turns out that that limit will either be positive or negative infinity. Just like if I were to plug in -3 over here, I'd have 1 divided by 0, I'm going to be in trouble, right? Can't divide by 0. But if I get very, very, very close to 0, what happens? This is going to be 1 over a tiny positive number, 1 over a tiny positive number is a large positive number. I think that's going to be approaching infinity, which is why we've got that vertical tangent line there. So it's increasing, it has a vertical tangent, and it's increasing again, and we see, using our graphing skills from pre-calculus, that the function has no relative extrema. And it's also consistent with the first derivative test. The function never changes sign, or the derivative never changes signs.